In a previous video, we went over how to take an arbitrarily shaped wheel and design a partner wheel for it so that both wheels can roll smoothly around each other without slipping. The results were some wheel pairs that sometimes looked like they could work as a pair of meshed gears. So it's tempting to think that the way to design gears is to treat them as two rolling wheels. Two shapes that maintain constant contact with each other and roll without slipping or sliding against each other. But this is actually completely wrong. It turns out rolling wheels and meshed gears are two completely different things, mutually exclusive, in fact. No rolling wheel system, except for two circles, can work as a gear pair. Or at least not as a gear pair that has the physical properties we usually expect. It also means that most actual gears you encounter in real life are intentionally designed to slide against each other a little bit. In fact, the usual physical requirements on gear behavior fundamentally require them to slide. Even ignoring design imperfections, it's mathematically impossible to design two gears that have no sliding action against each other. In this video, we'll look at why this is the case, and also develop a mathematical technique to design a genuine partner gear for any given shape. And if you're familiar with the previous videos about designing wheels for weird roads, we'll also see how this technique provides a way to detect and even mitigate the problem of road wheel clipping, where the ideal wheel for a given road could sometimes clip into the road, meaning the system couldn't work perfectly in real life. This video can be viewed as a follow-on to my Weird Wheel series, but it can be viewed standalone as well. Though if you want to be very well primed for this video, do take a look at that series, especially the third episode. Link in the description. Alright, now let's shift gears and get right into it. Take a look at this rolling wheel couple. Do you notice anything odd about its movement? If you pay close attention, you might notice how the motion is a little bit jerky. The wheels suddenly speed up and slow down as they roll over each other's peaks and troughs. This is because their angular velocities, the rate at which their angles of rotation are changing, is not constant. This is a problem if you're wanting to use these wheels as gears, since jerkiness in a mechanical system is usually something you want to avoid. Is there any way we can eliminate it? Well, kind of. If you think about it a bit, you might realize that you can actually tune the motion so that the angular velocity is constant for at least one of the wheels. Like maybe this purple one. After all, I'm the one animating this scene, and playback speed is something I can control. So in theory, I can tune the animation so that the purple wheel spins at a constant angular speed. But even though I can do that for the purple wheel, doing so makes the angular velocity of its partner very non-constant. It turns out it's impossible to simultaneously make both wheels spin at a constant angular velocity. At best, you can make one or the other do it, but not both at the same time. This is actually a consequence of the wheel coupling equations, the equations that govern the motion of smoothly rolling wheels on each other, which I went over in detail in a past video. The first equation says that the radii of the two wheels at the point of contact always add up to a constant, essentially saying that their axles always stay a fixed distance away from each other. The second equation says that the radius ρ of the first wheel at the point of contact times its angular velocity d phi dt is equal to the negative of the same product for its partner. This is essentially the rolling or no slip condition for the two wheels. Using the first equation to rewrite the second in terms of only a single radius function, we find the only way both angular velocities can be constant is if the radius of one of the wheels, and therefore the other as well, is constant. That is, the only way to achieve constant angular velocities for both wheels is if they are both circles. Any other wheel couple will require one or the other wheel to jerk a bit as they roll around each other. That's why it's impossible for two non-circular gears to roll smoothly around each other. The requirement of smooth rolling is fundamentally at odds with the requirement of constant angular velocities that gears usually mandate. If you're still not convinced, here's another way to see it. One of the consequences of two wheels rolling smoothly around each other is their two axles, and the contact point between them, always lie on a straight line at all times. This is what I called the radial alignment property in a previous video. But if you look at the motion of the point of contact between two real-world gears, you'll find that it doesn't usually stay confined to the line connecting the two axles. And whenever the contact point is off of the axle line, there necessarily must be some sliding action between the two gears. In fact, the distance between the contact point and the axle line might even provide a way to quantify just how much sliding is occurring between the two gears. But that's a little beyond what I know. Still, it goes to show how easy it is for misconceptions to sneak into your understanding of how things work and how the world is. It just feels right that gears should roll without slipping, even though that cannot be the case. And I've seen many people repeat this misconception online. Learning how to detect and prevent misconceptions and misinformation from taking root in your own mind is a skill I think is more essential than ever. And so if I can take a moment of your time here, I'd like to tell you about Ground News, this video's sponsor, who provides tools to help you think critically about and make sense of the media you consume. Created by a former NASA engineer, Ground News gathers and organizes news articles from a pool of more than 50,000 sources and lets you easily compare how they cover the same story, while also providing context such as where the bias leans, factuality, and who owns them. For example, for this story here, you can see there are about 20 articles covering it, and can see from this graphic that there's disproportionate coverage from right-leaning sources. It's interesting to compare headlines. On the left and center, we have the small number of cases emphasized, while on the right, you can find a stronger tone of alarm. Now, I know it's a bit ironic to say this in the middle of a sponsored segment about a tool to help you navigate biased content, but I really have been deeply bothered by the spread of misinformation online for a long time now, and I've been genuinely impressed with the tools Ground News have set up to help us think critically about what we consume, and I fully support their mission in that. I really do think many people will find these tools very helpful. Perhaps you. You can try them out by heading over to ground.news/morphocular, whereby you'll get 40% off their Vantage subscription, which is what I've been using. Link in the description. So thanks to Ground News for supporting this video, and now let's get back into it. Alright, so much for why rolling wheels can't function as gears. So how do we design actual gears then? How can we take an arbitrary shape and find the perfect shaped partner for it so both of them can spin around each other at a constant rate, while always maintaining continuous contact with each other? Let's look into that now. First of all, keep in mind that gear design is a very old problem, and so there are probably many approaches you can take to do it. I'm also not a mechanical engineer, so I won't know about many of the standard tricks of the trade here. But that said, here's one way to do it that I think is really cool and mathematically pleasing. First, let's frame the problem more precisely. Always a good first step. The task is to start with an arbitrary closed curve for the source gear and generate a partner shape for it so that both shapes can spin at a constant rate while maintaining contact between each other and not clipping into each other. We should also be given the intended distance between the axles of both gears, which I'll call r, as well as the intended angular velocities of both gears, since, as anyone with experience with gears knows, gear pairs can come in different gear ratios, meaning each gear can spin at a different angular velocity, though they both need to be constant. I'll call the angular velocity of the source gear omega, and its partner omega prime. So these are all the parameters we're given to start the problem. The shape of the source gear, the intended axle separation between the two gears r, and the two intended angular velocities for both gears, omega and omega prime. Now, remember how with wheels rolling on wheels, we could choose to frame the situation either as two wheels spinning in place, or as one wheel rolling around its stationary partner? Let's do something similar here for the case of a gear meshing with its partner. Take the source gear to be the moving gear, and the mystery partner gear to be the stationary one. In this picture, I'm actually drawing in the final shape of its partner to make things easier to see, but keep in mind, at this point in the problem, we're not supposed to know yet what the partner looks like. Now, since the angular velocities of both source and partner were given at the start, we actually already know precisely how the source gear will orbit around its partner. Its rotation speed is governed by the source angular velocity, omega, and its revolution speed is governed by its partner's angular velocity, omega prime. This is a big deal because it means we don't need to know anything in advance about the partner's shape to understand the motion of the source gear around it. Its motion is already fully specified directly from the base information we started with. Alright, great. But how does this help us determine the shape of its partner? Well, even though it's no longer visible, can you still kind of see it there from the motion of the source? It might help if I draw in some additional copies of the source orbiting around. Can you maybe kind of see a shadow of the partner there in the middle? As a matter of fact, the shape of its partner is completely determined by wherever the source never goes. That is, the partner gear is the negative space left behind by the orbiting source gear. You can see this more clearly if you imagine the source gear as being wet with paint, and as it moves around, it colors every location it visits. The boundary between painted and unpainted regions precisely describes the shape of its partner. Tell me that's not cool. Now, while this does work, it's a bit of an inefficient process, isn't it? I mean, to clearly see the shape of the partner, we have to draw a few hundred copies of the source gear along its orbit. That's not too hard to do with a computer at the relatively low resolution we're dealing with here, but it's not going to scale very well if we need a very high resolution plot of the partner. Plus, it's not totally clear how we can get the computer to automatically and consistently identify the negative space curve from this image anyway, or how to control the error in the approximation. So it'd be nice to have a more robust algorithm to generate this curve shadow without having to rely on drawing a picture and somehow eyeballing the resulting shape afterward. Luckily, there is a way to do just that. The thing we're looking for in this problem is what's known as an envelope of the source gear's orbit. Let's take a closer look at what envelopes are and how they work. Given an infinite family of curves, like, say, these line segments here, their envelope is basically the curve that forms the boundary between points in the plane that belong to some curve in the family and those that belong to none. In my analogy with paint, the envelope of this family of lines is the boundary between painted and unpainted regions as I continuously sweep through all the lines in the family. Now, our goal is to determine the shape of this envelope curve without having to literally draw in a zillion members of the curve family. But how can we do that? Well, first we can note that points on the envelope are also points in the curve family. So the envelope is composed of points taken from the curve family, but just a very particular subset of them. So what we need is some property or condition that will help us filter out potential envelope points in the curve family from those that aren't. The idea is similar to how local minima and maxima are found in calculus. To find potential input points that minimize or maximize a function, we set the derivative of the function equal to 0 and solve. The derivative equaling 0 is the condition that helps filter for these extremal points. So likewise, we need some kind of envelope condition that filters for potential envelope points. Can you think of one? Pause the video and take a moment to try and come up with something. Even if you don't hit the mark, I think it'll help you understand and appreciate the approach I'm about to showcase. I'll wait a second. Okay, it'll help if instead of thinking about all the lines in this family all at once, we just picture a single line which changes over time. So at time, say, t equals 0, the line looks like this. And at time, say, t equals 1, it looks like this. And at t equals 0.5, it's somewhere in between. So we're basically indexing all the lines in the family with a continuous parameter t. Likewise, given the line's state at time t, we can select an individual point on the line with another parameter, maybe call it s. So the two parameters, s and t, can together specify a single point in the family of curves. T selects a particular curve in the family, and S selects a particular point on that curve. We can encapsulate this scheme as a single function I'll call gamma, which takes S and T as inputs and outputs a single point in the 2D plane. With this setup, our goal becomes to filter out what combinations of s and t values may produce envelope points. To that effect, let's take a look at an arbitrary point on the envelope, and let's say its parameter coordinates are s0 and t0. Now, think about how this point could move if I slightly nudge one of the parameter values away from s0 or t0. In what direction could the point move? Well, one thing's for sure. The point certainly can't move in a direction pointing into the negative space beyond the envelope, because, by definition, the family never goes there. So it can only move either back toward the interior of the curve family's range, or else move parallel to the envelope. But here we can make a curious observation. Velocities can always be traced both forward and backward. So if varying a parameter in one direction causes the point to have a velocity pointing toward the interior of the curve family, then varying that same parameter in the opposite direction will cause the point to move away from the family's range and into the impossible region beyond the envelope. So really, there's only one possibility for the point's velocity. It must point in a direction parallel to the envelope curve. And critically, this is true regardless of which parameter, s or t, we choose to vary. Either way, an envelope point's velocity must point in a direction parallel to the envelope curve itself, meaning the two velocity vectors we get from varying either s or t will be parallel to each other as well. This gives us a way to write down a condition that all envelope points must satisfy. The velocity vector from varying the parameter s can be described as the partial derivative of gamma with respect to s. And likewise, the partial with respect to t describes the velocity vector for varying t. And at an envelope point, we must have that these two derivative vectors are parallel to the envelope curve and hence parallel to each other, which we can mathematically describe by saying their 2D cross product is 0. If you haven't heard of it before, the cross product is basically a way of measuring how perpendicular two vectors are, with it equaling 0 for parallel vectors. And it can be computed with the following formula in terms of the x and y components of gamma. This is our envelope condition. Any point in our curve family that is an envelope point must satisfy this condition. To see how to use it to actually compute an envelope curve, let's get specific and find a formula that will reproduce the red envelope for this family of line segments. In the case of our line family here, its gamma function can be described with the following formula. You can see that if t equals 0, its x component becomes constantly 0, corresponding to the leftmost vertical segment, and if t equals 1, its y component becomes constantly 0, yielding the bottom horizontal segment. All the other t values give us some mix between the two. Now, let's compute all the partial derivatives of gamma and take their 2D cross product and set it equal to 0. And now, with a little bit of algebra, I can solve for s as a function of t. Substituting this back in to the original function for gamma of s and t, we get its envelope is described by the following parametric function of t. And sure enough, if I get the computer to plot it, it fits in perfectly. So we now have a robust algorithmic way to calculate the envelope of any family of curves directly from its parameter function gamma. Let's see if we can apply this to generating gears. To use this technique, we first need a way to express all the different states of the orbiting source gear as a parametric function gamma of two parameters s and t, where, remember, t is a time-like parameter indexing the states of the gear in its motion, and s indexes for a specific point on the gear in that state. Since the motion of the source gear involves a lot of rotation, it'll probably help if we describe the gear and its movement using complex numbers, which are famously useful whenever rotation or circular motion features prominently. Don't be scared by that though. It just means encoding the x and y coordinates of points in the plane as the real and imaginary parts of complex numbers. To start, I'll let the complex valued function f of s be a parametric description of the source gear within its own local coordinate space, where the axle is located at the origin, or 0. So as the real number parameter s varies, f of s traces out the shape of the source gear in this local coordinate space. With this in hand, we can start to describe its movement over time like this. First, the source gear is rotating according to its own angular velocity omega, meaning after t seconds have passed, the source will have rotated by omega times t radians. We can account for this in our expression by multiplying our local f of s function by e to the power of omega ti, which is an expression that has the effect of rotating a point by omega t radians counterclockwise around the origin. So we've now accounted for the local rotation of the source gear. Now let's start to move it into position in partner gear space, where the envelope we want to find lives. In partner gear space, the origin is the axle of the partner gear, and the source axle always stays a fixed distance r away from it. So we need to move our spinning source gear a distance of r away from this new origin point. That's pretty straightforward. Just add the real number r to our expression to shift the gear r units to the right. Finally, we need to account for the orbital motion of the source gear around its partner. That orbital motion is controlled by omega prime, the intended angular velocity of the partner gear. So we need to revolve our spinning source gear by omega prime times t radians around the origin to account for this. Once again, complex numbers make algebraically encoding this simple. We just multiply our entire expression by e to the power of omega prime ti. And there you have it, a complete parametric description of the source gear's motion around its partner. This will be our gamma function whose envelope we want to compute. To do it, we'll need the two partial derivatives of gamma with respect to s and t. I think it's nicer to do this if we first distribute the omega prime exponential. Now we need to take the 2D cross product of these two partial derivatives. Normally that would mean breaking them up into their x and y components, but there's actually a sneaky way to do it just using standard complex number operations. Turns out, if you take the conjugate of a complex number z, meaning you flip the sign of its imaginary part, and multiply it by another complex number w, the real part of the result will be equivalent to the dot product of z and w as vectors, and the imaginary part will be their 2D cross product. I'll leave it to you to verify this if you want. The upshot is we can take the 2D cross product of our two partial derivatives without having to split it into components. In this case, I'll take the conjugate of the partial in s and multiply it by the partial in t left alone. The imaginary part of the result will be the 2D cross product we seek. Now we just set it equal to 0 and solve for one of the variables. It actually doesn't matter which variable we solve for in terms of the other, and in this case, since the variable s is stuck inside an arbitrary function f, it'll actually be easier if we solve for t in terms of s this time. Unfortunately, from here on, the algebra becomes a bit of a mess. I'll put the full derivation on screen for a moment for the committed among you who want to pause and go through all the details, but in the end, we arrive at the following formula for t, where phi of s is a continuous function returning the complex angle of the derivative of f, and alpha of s is shorthand for this giant inverse cosine expression. Now, even though it's kind of an algebra nightmare, it is nevertheless a closed form formula, which honestly really surprised me. I was expecting somewhere in the process there'd need to be a numerical equation solving step, since the shape of the source gear is arbitrary. But you actually don't. You can solve it with pure algebra, which kind of blows my mind. Plugging this formula in for t in our gamma function gives us a parametric description of the envelope of an orbiting gear. Now, something you might notice about this formula is the plus or minus that shows up here. That actually reflects the fact that an orbiting gear actually has two envelopes, an inner and an outer envelope. In our case, we're interested in whichever solution yields the inner envelope. I don't think there's a way to tell beforehand which sign, plus or minus, corresponds to the inner envelope, So in practice, what I do is I evaluate both at just a single arbitrary s value and see which sign produces a t value that lands closer to the origin when plugged into gamma. The sign to use should be the same for all values of s, so this comparison only has to be performed once. But yeah, that's pretty much it. Using this technique, you can find the partner gear for any given shaped source gear. Let's take a look at some fun examples. Let's start things off with a classic, a square gear. At a source to partner gear ratio of 2:1, we get an 8-petaled clover. Some of you might notice that this partner looks pretty similar to one of the partner wheels for a square that rolls around it. It's not a perfect match, but it does come remarkably close, doesn't it? My guess as to why is that a square is close enough to having a circular shape that it approximates having a constant angular velocity pretty well even when it's rolling. As for other polygons, like triangles and hexagons, the results are pretty similar, more clover shapes, though the triangle's partner has deeper cusps. Next up, here's an ellipse with its axle at its center. And the same ellipse, but with its axle at a focus point. This one is a little weird, since the ellipse is kind of imbalanced, and the side of the ellipse furthest from the axle moves quite quickly, requiring the axle separation to be rather large in order for the envelope algorithm to work. Right now, the axle separation is set to 3 units, with the ellipse's long diameter being 2 units, but if I reduce the separation to 2.7, you can see the envelope algorithm starts to produce some odd little artifacts around the cusps. And if I go further and reduce the axle separation by very much more, it just outright fails to render due to trying to compute the inverse cosine of a number greater than 1. To be honest, I'm not 100% sure why this occurs, but when you look at the motion of the orbiting ellipse in this case, you can see how its far side kind of swings in a direction opposite to the orbital motion at certain points. And so it wouldn't surprise me if this backward movement wreaks a little havoc with our envelope algorithm as we've defined it. Anyway, that's something to keep in mind about this envelope algorithm. It is somewhat sensitive to how the initial parameters are tuned. Luckily, it does seem to work for most normal configurations. But yeah, if you tune the parameters to weird values, the algorithm will break down pretty quickly. Speaking of playing with the parameters, by setting the source and partner angular velocities to have opposite signs, you can actually use this technique to create internally meshed gears, where the source rolls around the interior of its partner. In this configuration, the source gear revolves in a direction opposite to how it spins. In this animation, it orbits counterclockwise, but the gear itself spins clockwise. However, note that in this case, we need to take the outer envelope of the orbiting source gear, since the partner gear curve would be further away from the origin than the source gear. Finally, let me remind you all again that more goes into gear design than just what I've shown. I've been focusing on satisfying the constant angular velocity condition of gears, but there are many other things to take into account when designing real gears for real use, such as how to minimize friction and wear and tear, optimizing force transmission, and so on. How to take these other considerations into account when designing gears is beyond the scope of this video and my expertise. But isn't it delightful how the seemingly daunting problem of designing a partner gear for a given source gear can be solved with a slight change in perspective and the simple but surprisingly powerful concept of envelopes? But envelopes actually have one more gift to give us. If you watched my video series on weird wheels, I mentioned how some road wheel couples couldn't be physically realized perfectly, since some wheels will clip into their ideal roads at certain spots in the roll. One example was a triangle wheel, whose corners collide with its road prematurely. Now, if you're an engineer or programmer at heart, you might wonder how we can detect when this will happen and if there's a workaround to this issue. Turns out there is, and envelopes are just the tool we need. By calculating the lower envelope for a wheel rolling on its ideal road, we can check for any segments where the envelope dips below the road curve. If there are any, then the wheel must clip into the road there. But what's even better is the envelope provides a snazzy way to remove the clipping as well. All we have to do is replace the road curve with the envelope curve wherever the envelope is beneath it, and we'll have eliminated the clipping while changing the road minimally. Basically, think of the envelope as a knife that cuts out the exact parts of the road curve that collide with the wheel. Doing this, we can finally get a road which a triangle can roll smoothly over in our actual physical real world. Or, well, at least mostly. Since we did remove segments of the original road, it means the wheel will no longer roll completely smoothly over those segments. But if the removed segments are pretty small, I think it could still work out pretty well. And with that, I think I'll call it a video. I'll leave you with some pleasing animations of partner gears being carved out from their orbiting source gears. Enjoy!